Logarithmic functions are they're the inverse of exponentials. They're how we're going to solve them. So, for example, let's say I knew that 1024 was a power of 2 to some power. Well, we can rewrite this as a logarithm. So what ends up happening is this exponent is going to be the result of a logarithm, and we have to tell the logarithm what base to look at and what we're trying to evaluate. And that's what a logarithm does, is it gives you the exponent needed. So here's the actual definition of it. If we have this, I'm going to write it bigger, a to some exponent y equals x, then y, the exponent, would be log base a of that x, of whatever that the end result was. So in other words, log base 3 of 81 is going to be 4, because 3 to the 4th power is 81. Let's just practice going back and forth. So if I know that 64 is 4 to the 3rd power, the logarithmic form would be log base 4 of the 64 equals the exponent. So this is always the exponent, and this little number is always the base. What if I was given a logarithm? Could I write that as an exponent? Well, the base is 4, the exponent is -3. So this could be written as 4 to the -3 equals 1 over 64. If 4 equals log base 2 of x, so the exponent is 4, the base is 2, this really means 2 to the 4 equals x. Well, that means x is 16. What would log base 2 of 8 be then? Well, this is actually finding, let's make that equal to x. If I rewrite that, that's 2, the base, to what exponent gives me 8? Well, that is 3. What would be the result of the logarithm here? Remember, the logarithm is giving me the exponent. The logarithm is the exponent. So, base to the exponent equals 1 over 25. So what would give me that fraction? It'd have to be a negative exponent. 5 squared is 25. This would have to be -2. Now let's get a look at what the graph would look like. So I did tell you that the logarithm and the exponential are inverses, and they are. So let's think about, so this is base 2. Let's think about y equals 2 to the x. And I'm going to make a smaller table than what we had in the previous lesson. Let's just go from -1 to 2. This would be 1, 2, 4, 1/2, and 1/4. If I'm switching it, and now it's y equals log base 2 of x, that means y is going to be the exponent and x is going to be the result. So if you remember your inverses, we're literally going to just switch our x's and y's. So now 1/4 goes to -2, 1/2 goes to -1, 1 goes to 0, 2 goes to 1, 4 goes to 2. I end up with, it almost looks like an exponential, but it's kind of twisted. The exponential would have been going like, let me do it in a different color here. The exponential would have been doing this, and my logarithm is the inverse, so it's doing the opposite. Just to show you real quick, this could also be done in the calculator. Let me turn off all those goodies. Whoops, I gotta turn off the plot. Now, if you are using one of my calculators or using Desmos, we can actually pull up logarithms in here, and not this log. This is a special log. It's log base 10. If we go to alpha window, there's one that says log base, and it leaves you a place to put the base and then to put what's in the parentheses. This time it's just an X. And let's, whoa, my window's off. Let me go to zoom. Hold on. Oh, it's still spinning. Oh no. Okay, zoom, standard, goes back to that 10 by 10 window. Now notice it does not show me this part of the graph that was going down here because it's so vertical. You see how like up and down that is? That the calculator can't see it too well. It's putting it there, but it's getting mixed up in the pixels. So there's two special logarithms. I mentioned one of them just a second ago. Since we live in a base 10 world, just a log by itself means log base 10. And that one is on every calculator. Now log base E is called a natural log. And it's actually French logarithme naturel, so that's why it's LN. And that is on any calculator. Doubling time for an investment. If P dollars is invested for T years at interest rate R compounded continuously, then the future value is given by this function. So P is how much you invested, R is the rate, and T is the number of years. The doubling time for this investment can be found by solving for T in this equation when our new value is twice P. So let's think about that. If we're doubling our investment, then we're looking for when our investment is twice as big as what we started with. So here's the formula, and here's twice our investment. Well, if I divide both sides by P, I get 2 equals E to the RT. And we're trying to find the time So if I solve this, I'm going to rewrite as a logarithm. So this is base E. So technically it would be that log base E of 2 equals the exponent. Now log base E, that just kind of looks weird. So I'm going to call that ln. And we're solving for T. So let's say we had %. So let's say our rate was, so we're going to have our rate and our time to double. Let's investigate this a little bit. So if we had 10% or 0.10, I'm going to show you how to do this on the calculator. Go to the home page, I'm going to pull up a fraction. It said ln of 2 divided by the rate. And I get 6.93. If it was 20%, ln, which is on my calculator right below the word log next to 4, of 2 divided by 0.2. It's basically 3.5. To make this clear, I'm going to do 7%. So that would be 0.07. Gives me 9.9. In economics, you can find this doubling time with a little shortcut. It's called the rule of 70. If I take 70 divided by the percent, you're going to get a good approximation. This is the rule of 70. So 70 divided by 10% would give me close to 7. 70 divided by 20% is going to be 3.5. 70 divided by 7% would be about 10. So this pattern actually has a little shortcut rule to it. All right. And since we were dealing with ln, let's look at the graph of ln. So I'm going to actually just put this in the calculator and let's take a look at it. So ln of x, clear ln of x. Notice that it's going through 1, 0, and then it's kind of, this would be about at here. And so it's doing this number, right? And then it just looks like it stops there. It doesn't. It's going to keep going, but it's almost a vertical line right there. So I want you to realize that it should keep going. But so notice that all the logarithm graphs kind of look the same. So graphs of logarithms always end up looking like this, and they're always on this side of the y-axis, always. So my domain is all positive real numbers. So we can only take the logarithm of a positive number. And I don't know why I jumped to example 5. I don't know what happened to example 4. It's okay. Now let's look at modeling. So the expected lifespan of people in the United States depends on the year of birth. And we've kind of seen that happen before. If we do the scatter plot, it ends up looking like this, which could be a logarithm. Linear wouldn't work so well. So what we're going to do is we're going to type this into stat. I know you don't want to sit here and watch me type in all of these values, so I'm going to speed this up. I'm going to press pause. So I typed in all the data. If you have not done that yet, press pause and do it. Highly suggest it. Now I'm going to look at the scatter plot, so I need to clear out anything there. Turn on plot. Press zoom 9 for stat, and we get the same picture. Thank goodness. Now we're going to find a logarithmic equation that will model that data. So I'm going to put my calculator on this side. So to find a logarithmic equation, we're going to go stat calc, and we're going to scroll through. So notice here's ln. The calculator uses natural log to do this. So we're going to press ln. We'll store it in y1 so we can make sure it's a good fit. And it's going to give me an a, which is 11.03. And it gives me a b, which is in front of the natural log, 304, natural log x. Let's see how good a fit that is. It's a perfect fit, I think. Now, the National Center for Health Statistics projects the expected lifespan for people born in 2000 to be 77, and that for those born in 2010 to be 78.1. So the year 2000, so this was started in 1900, that'd be plugging in 100. So let's see what, 100. And 2010 would be 110. Let's see how close our equation is to getting those. So I'm going to do this a different way. I'm going to go alpha f4, y1 of 100 gives me 76.9, and y1 of 110 gives me 78.3. How close are those? Well, 76.9 is pretty darn close to 77. 78.3 is pretty close to 78.1. Could the expected lifespans for 2015 and 2020 have been found with the model found in Part A? Let's see. So 2015 would be 115, and this would be 120. That's exactly what they got on the table. So not only are they close, they're exactly the same. All right. Sometimes we're going to need to use some properties of logarithms. That's going to be in a little separate video. So there's going to be a part 2 to this because this is a fairly long section.